Okay, so in my pre-calculus class, since you're tutoring pre-calculus students, you should know this anyway, we observed water flowing out of this little tube here. Time it takes to get here, 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 here. Okay, there are 5 points. I'm only writing 4 here, but it would work just as well for 5. Okay? So the data points we get are like 10 seconds, 140 millimeters. At 10 seconds, the water was 140 millimeters above the tube. 40 seconds, 90 millimeters. 90 seconds, 40 millimeters. 150 seconds, 10 millimeters. We want to model AT squared plus BT plus C that comes as close as possible to fitting these points. Now 3 points, you can solve simultaneous equations and get a quadratic. You got 4 points, too much information. You can't get an exact solution. So we can write out what these points tell us. If the model is this, then 140 equals 100A plus 10B plus C, just plugging in 10 for T, 140 for Y. Do the same thing for this point, this point, this point. We get 3 more equations. These equations can be written as a matrix equation. Okay? And what we're trying to find is A, B, and C, but there's no solution. These row vectors are all linearly independent. That's obvious if you look at it. Okay? Well, not totally obvious. But if you reduce the matrix, you do end up with a row of zeros. Okay? And I said the row vectors are all linearly independent, which is obvious, which is a lie. It wasn't. It's obvious they aren't. They can't be. And you can think about why. Okay? Never know what's going to come out of my mouth. It starts in my head somehow. Okay. So anyhow, we got this. And what we want to get is an A, B, and C that gives us a model that fits this data as closely as possible. Okay, well, okay, this is an inconsistent system. We want to find A, B, and C such that what? Such that we multiply this matrix by the ABC. What we get is as close as possible to this vector. Okay? So, well, we can depict this. We're mapping from R3 to R4. So obviously there's going to be a null space of the inverse over here. The column space is going to have dimension 3. And that is pretty obvious. But if you want to reduce it, to prove it to yourself, you can. We've got a row space here, which turns out is all of R3. Okay, a null space, which is the empty set, because the rank is 3, nullity is 0. Okay? I'm designating the transformation by its matrix A, so we're going to call that the A matrix. So the column space has dimension 3, you got a null space here, dimension 1. Okay, so null space is basically a line in 4-dimensional space. Okay, now this thing that you get when you multiply any ABC by this, you're not going to get this. You can't. Okay, you don't have enough variables here. So this is not in the column space. It's out here somewhere. Okay. Now we have the direct sum thing. You know, this space is a direct sum of its column space and its row space, meaning that any vector here can be uniquely represented by a vector in here and a vector in the null space. Sum vector in the column space and a vector in the null space. Okay. Anyhow, it's not in the column space. You have the null space of A transpose here, column space here. Okay, so they're not in the column space because it's an inconsistent system. You can't get this vector. But what you do is you project this vector to the column space. And that projection is going to give you the vector that's as close as possible to this one. Over here, then you find out what vector that came from over here. And that's the A, B, and C that gives you the best model. So, we can kind of represent that by picture. Here's A of it's not A of 140. You don't apply A to this vector, you apply A to this vector. Okay? Get your 140, 90, 40, 10. And here's your projections of column space. And this vector here is in the null space. Because of course, this vector can be uniquely represented as a vector in the column space plus a vector in the null space. Okay?
Okay.
And that's an orthogonal projection in Euclidean space. Okay, well, that's what we're going to do, but we want to do it in general. We don't want to confine ourselves to R3 and R4, okay? We want to be able to do this symbolically in terms of matrix A. And a target vector over here. Okay? So, we're going to go on and state that. Let's go ahead and state the problem. So when you have a set of data, and the dimension of the model, it's going to give you AX equals B. Okay? You want to do a cubic polynomial with more than 4 points? Do it. Okay? Whatever dimension. Okay, so we have AX equals B, where the equation is inconsistent. In other words, no solution. We find the x that lands us as close as possible. To B. That's the problem. And it's just, as I said here, again, the strategy is simply find the vector of the column space that's closest to B. This is going to be the projection of B on column space. Okay. The projection will be along a vector in the null space of A transpose, because your codomain, the space in which you're mapping everything, is a direct sum of the column space and the null space of the transpose. Okay? So that's all there is to it. And of course, we're still going to picture it like this. And that picture is going to be helpful.